A naive brute force approach to solve this problem would be to exhaustively enumerate all possible acyclic paths from the source to the destination and pick the one with the smallest cost. Let's see how much time that would take on a sample directed graph like this one. I have omitted out the weights from the edges because I just want to make the point that there will be an exponential number of paths if we actually try to count how many paths there are. So it doesn't matter what the weights are. If we have an exponential number of paths to enumerate, this is not going to be a practical solution on even moderately sized inputs. So when we start from the source here, any path could either choose to go up or to go down. In either case, sooner or later we'll converge at this vertex, and then again we face the choice of whether to go up next or whether to go down next. So at each of these yellow nodes here, we face this choice of whether to go up next or whether to go down next. So if the number of nodes in this graph, the number of vertices in this graph was n, I can cluster together all the vertices in successive groups of 3 like this. This is the first group. These are the first 3 vertices in the first group. The next 3 vertices go into the second group. The next 3 vertices go in the third group, and so on. I can continue like this until I have these 3 vertices classified into one group, and then we have this lone vertex, the destination vertex, which doesn't fall into any group. So if we group together the vertices like that, we can see that the total number of vertices is going to be that lone vertex at the end, 1 plus some number which is going to be a multiple of 3, because we have 3 nodes otherwise classified into each cluster. And I'm assuming there are I clusters. So this is the first cluster, this is the second cluster, this is the third cluster, and so on, and this is the ith cluster. So any path from S to D is going to involve making I different choices at these nodes, at these I nodes, each choice being whether to go up or whether to go down. So in how many different ways can we make these choices? We have I choices to make in total. At the first fork we have 2 choices, at the second fork we have 2 options, at the third fork we have 2 options, and so on. So there are 2 raised to the power I different ways to make this sequence of I choices, and each sequence of I choices corresponds to a unique path from S to D, which means the total number of paths from S to D is going to be 2 raised to the power I. Now I itself is roughly speaking n by 3, right, because n is 1 more than some multiple of I, so I is going to be n minus 1 divided by 3, which is roughly n by 3 if n is large. So I can write 2 raised to the power I as 2 raised to the power n by 3 approximately, and this in turn can be written as the cube root of 2 raised to the power n. Now the cube root of 2 is a number that's more than 1, it lies between 1 and 2, and so whatever this number is, it's clearly exponential in n. So if we try to follow this approach of enumerating all the different acyclical paths from S to D, we are going to end up enumerating an exponential number of paths. So basically we get a combinatorial explosion if we follow this naive exhaustive enumeration approach. Now this should remind you of the combinatorial enumeration problems that you must have done earlier. Notice that any path from S to D is really a permutation of vertices which starts at S and ends at D. So this approach is really a combinatorial enumeration approach where we are enumerating all the different permutations of vertices which start from S and end at D, but which may or may not include all the vertices. And our goal is to pick that particular permutation, that specific path from S to D, whose total cost is minimum. So we want to pick the best possible permutation which has the least cost, and that identifies this problem class as combinatorial optimization. So finding the shortest path from S to D in a graph is basically a combinatorial optimization problem, for which you must have studied techniques earlier like dynamic programming and the greedy approach. In fact, the previous problem that we studied, which was the minimum spanning tree problem, was also a combinatorial optimization problem, because there we had to build a spanning tree. A spanning tree was basically a subset of n-1 edges formed out of the m edges that are given in the graph. So out of the m edges, we had to choose n-1 edges, and we had to specifically have those edges be a spanning tree with the least cost. And I mentioned there also that if we were to try to exhaustively enumerate all possible subsets of n-1 edges, checking if each subset is a spanning tree or not, and if it is, then noting down what the cost is, and then at the end figuring out which subset of n-1 edges has the minimum cost, that would also be an exhaustive enumeration approach to solve a combinatorial optimization problem. But we saw previously that by following a greedy approach, in fact we had two different greedy approaches that worked in solving the previous problem, the minimum spanning tree problem, and so we want to see whether we can come up with a greedy approach to solve this particular problem. So here is one possible greedy approach. We start from S, we want to figure out the shortest path to D. So we look at what are the different options available to us. So let's say we have three edges out of S with weights 1, 2 and 3 respectively. Well, it's clear that this edge of weight 1 is the cheapest edge, so let's follow that, and let's say we come to this vertex, and again we might have 2 or 3 options here, and we will again follow the edge which has the cheapest cost, and so on. Is this strategy going to lead us to the shortest path from S to D? Well, let's take this simple small graph here. Let's say we start from S, and according to this strategy we're going to pick the edge of weight 1 to next go to. So we are growing a path which we are claiming might end up being the shortest path from S to D. Now from this vertex we have no choice, we have to follow this edge, and we end up at D. But you can already see that this is not the shortest path from S to D. The shortest path from S to D would go like this. And notice that the very first step the shortest path took was to follow an edge that was more expensive than the edge that we followed. So it's not necessary that at each step we have to pick the cheapest edge to elongate the path. In fact, it's possible that the cheapest edge out of S might be a dead end. It may not even lead anywhere. Maybe D lies somewhere over here, and this edge had a weight 1, this edge had a weight 5. If we followed the greedy strategy, we would end up at a dead end. So clearly this particular greedy strategy is not going to work.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today